video. Hey guys, I am recording this in the corner of the airport, just waiting for my flight because it got delayed by 20 minutes. I got my Totoro here that I take with me on all of my flights, and so I'm recording this video for you guys so you have it ready to go on Monday. So this video is for you guys to follow along with, to just kind of check through your lab as you're going through it and making sure you're keeping track of a couple things. So first off, with your SketchUp labeled setup, this is a bit more of a complicated setup. So I just want you to kind of look through this really quickly and make sure that you did all these things. That when you do your SketchUp label setup, every equipment that's listed, you do want to draw within reason. So you don't need to draw like every single mass. You don't need to draw like the wax paper or the aluminum foil necessarily. But what you can do is when you label your stuff, you can point to the block and say, will change surface with wax paper and aluminum, or will add masses onto the top of the block. And you want to draw the setup again, how it would be before the start of the experiment. So where would you have the block? How does the spring scale look? All that. And again, just double check and make sure that you labeled each piece of the equipment that's listed. So take a second, you can pause the video, go check your sketch, make sure you have all of those things. Now let's get into the meat of it with the procedure. So with the procedure, skim through it first. You don't want to write a procedure with any pronouns. So you, I, we, they. You shouldn't say that I did or we did or you should do. Just say do this, do that. Yeah, there's no pronouns needed whatsoever. So read through. Again, the easiest way to change something is to just remove the I or the we. Do this, do that. Don't say I. I don't think anybody did bulleted last time. But just want to make sure you number the list, not bulleted the list. For this particular lab, make sure that you said somewhere how we determine the normal force. We didn't measure the normal force directly. The normal force was calculated, right? We measured something else and then used that to get the normal force. So you need to list that as a step. You need to say, how did we get the normal force? We ended up graphing the normal force. How did we get it in the first place? So make sure you say that as a step. Now you guys have to be careful with this. Did you specifically say how you would record the data and specifically when to record it? On your last lab, a lot of you guys just said like, let the car go. And then didn't say like what to do to record data. Some of you guys even didn't say like, you said let the car go and drop sugar packets. Well, what are you recording and when? Now for this lab, you had the directions right above the procedure. Let me see if I can pull it up still. Oh, I don't have the lab up here. Let me see. There we are. Right above the procedure, there was instructions for how to record the static friction and the kinetic friction. So you can feel free actually to just copy right there. To copy and paste those directions where they should go into the lab. You don't even need to rephrase them necessarily, as long as they make sense and like fit in at the steps where you should. So please be very clear on how you're recording data and when you will record it. Will you do something first and then record it? Make sure that you included a step to it. You always have to. Even if I don't tell you, you have to. You always have to include a step to account for experimental error. So you need to state somewhere in there that even though we're only recording the friction force one time per mass, you want to try it a couple times to get consistent results and then decide what to go with. So make sure you state that somewhere in your procedure. And then did you end your lab? A couple of you guys missed this last time by stating what graphs would be created with the data specifically by title. So you need to say, you will then take the data and plot this versus that, this versus that, this versus that. There was 6 graphs. How you know what graphs you're doing is in the lab document. So again, look back over your procedure. Make sure you did all of these things. And then I'll come back to the video. We'll keep going. Okay, data. There was 3 data tables. You need to copy, when you guys copy over your data, you copy all the original data, not just the data that you graph. Everything, the entire data table, that goes in. So make sure you did that. That's really the only thing. A couple of you guys lost points last time because you only copied the data that you graphed. You didn't copy the whole data table. So in your graphs, there were 6 graphs. 2 for wood on wood, 2 for wood on wax, 2 for wood on aluminum. make sure you have all 6. Each graph needs to have a title, which again is what versus what, your dependent versus your independent. Axis labels with units on the axes, line of best fit, and the equation. Remember, in Canvas, there is a document titled Graphing in Google Sheets. If you're not sure how to do any of these things, reread that document. There is plenty of people in class, even outside of your lab group, who know how to get a line of best fit and the equation as well. If no one in your group knows. So pause the video, go finish your graphs, and then you can come back and I can talk you through the analysis. Okay, so in number 1, it says, what are some possible sources of error in this experiment and their effects on your results? You can't just say human error. Yeah, it's because that could be so many things. So be specific. There is something that I talked about with you guys about the fact that when we're talking about wax on wood, what we're actually looking at, what I'm going to show you here, is like flat wax, not wax paper. If I say aluminum on wood, what we're actually talking about, or what we would like to actually look at, is completely flat, solid aluminum that's not going to move. So talk in your group and think about some possible sources of error that had to do with our materials. There are quite a few that you could think about. List them specifically. Pause the video, answer that question, come back. Okay, so it says, knowing what we know about the relationship between the normal force and friction force, what quantity is indicated by the slope on the graphs on 3, 5 and graphs 2, 4, and 6? So here's what I wanted to talk through with you guys. All of your graphs should have the, I forgot to keep my finger here, the normal force on the x-axis. Come on, friend, you can do it. There we go. Normal force on the x-axis and whatever friction force on the y-axis. So what this is then, when you look at your equation, right, you have always, this is going to be y equals mx plus b, right, for whatever equation you got. So if we notice, again, what is on our y-axis? The friction force. And then I have my slope, whatever your slope happened to be based on your data, right? And then we have our x, which was, if we look at our graph, what was on the x-axis? The normal force. Now, the plus b, very often, guys, this only will occur on our graphs because of the error that we get from the graph. So really what we have is this. This should look familiar to you. This is the formula for friction, right? If you look to your notes, this is the formula for friction. If that's the case, what does that mean your slope represents here? Look at the formula for friction. Look at what goes next to the normal force. What does our slope have to be? Well, the formula for friction is mu times the normal force, which once again is the coefficient of friction. So when you look back to the analysis questions, scrolling. Look back to the analysis questions. It said, knowing what we know about the relationship between normal force and friction force. Well, what we know is friction force equals coefficient of friction times the normal force. So our slope is the coefficient of friction. Now it's the coefficient of friction between those two surfaces. And not only is we have a coefficient of friction for static and a coefficient of friction for kinetic for each kind of surface. The second part of this says, what are the units on the slope value, if any? So let's look back to our graph. We know the units for slope are always y units over the x units. So I want you guys to think for a second. Look at what's plotted. What are my units for my y-axis? What are my units for my x-axis? My y units, well, it's friction force, and force is measured in newtons. Normal force is my x. Well, that's also measured in newtons. So what's going to happen here? Well, that's going to cancel. So what this means is the coefficient of friction, mu, actually does not have any units that measure it. All it is it tells us that friction force is some multiplier of the normal force, or I should say some fraction of the normal force. So you want to explain that. You want to explain this part, the fact that my slope is going to be newtons over newtons. Back here for y. So it says, what are the units on the slope? Well, there's not any. Explain why. And then pause the video, come back when you're ready. Okay, next question. Which factors influence the force of friction? This should be pretty obvious. We changed a couple things throughout this lab. In fact, we actually changed two things. What two things did we change through this lab that caused different changes in the force of friction? Talk to your group. We changed two things. Those factors influence the force of friction. Pause the video, answer that, and come back when you're ready. Okay, so let's talk about percent error on this last analysis question. So we haven't really talked about percent error. You may have seen this in other labs and other science classes, but what a percent error does is it compares the data you found to what we know to actually be true. So here you are going to copy over your coefficient of friction for static. So be careful, take a second. Look at your static friction graphs. We just said again that the slope is your coefficient of friction. So take a second, go to your three graphs, look at your slope on the static friction graphs, and copy the slope here, here, and here for wood on wood, wood on wax, wood on aluminum. Okay, you're going to do the same as well for the kinetic friction. So look at your kinetic friction graphs, look at their slopes, copy them over. Okay, so from there, now what I'm telling you is the known values for coefficient of friction for wood on wood and kinetic there as well, wood on wax and wood on aluminum. Now, when we say these are the known values, these are the accepted ones that we have found by very exact experiments like this one. Yeah, experiments like this one that use much better materials. Yeah, again, our little spring scales are not very exact. We're like, that's about this much. Yeah. Scientists have done very exact experiments just like this, though, to determine the coefficient of frictions. So let's say, for example, that my coefficient of static friction I found for wood was like let's just go ahead and make something up here. I don't even know, 0.10. Sure. So this is what we know to be true. This is what you found in your experiment. So what you're going to do is you're going to plug into this formula for percent error. Oops, that was supposed to be an eraser. There we go. So here's an example I'm just going to show you. So what your percent error does is it finds how far off you were again in error from what we knew to be true. So if my value was 0.10, I'm going to put that there. Sorry, I yelled a lot today at the homecoming game, guys. The known value was that 0.5 over the known value 0.5. So I just plugged everything into this equation here. I'm going to multiply that by 100 because doing the division will keep it as a decimal. Timesing it by 100 gets it to a percent. And then I'm going to put my answer right there. Do not freak out. A lot of you guys are going to have very high percentage errors because, again, our equipment was not very exact for one, as well as if your aluminum wrinkled at all, or same for the wax paper, that's going to throw stuff off. That's things you could have talked about in number one that can throw stuff off. Okay, so once again, pause the video, do all of your percent error calculations. Again, if you are off by like, don't be surprised, 300% error. I had some last year like that. I'm not grading you for that. It just means that you might not have been super exact in your data collection, but not a big deal. Okay, so pause the video, complete that, and then come back and we will finish up by talking about the application problems. Okay, so you still need to do the conclusion where you need to write about what you learned. You need to write in complete sentences at least two things in complete sentences. Yeah, it says bullet points, but you're just bulleting this and this in complete sentences, at least two things. Let's go ahead and look at the application problem. So I'm just going to kind of give you some hints on this one, and then I might talk about it on Wednesday if anybody's not certain of the answers for this. Um, so it says, if this lab were to be conducted again on an inclined plane, explain the effect on. So when I say effect, we say, how is it going to change? Yeah. These things are either going to increase or decrease. So what you need to do in order to know if it's going to increase or decrease, what you need to think is, what is it on a flat plane, which is the experiment we did, right? We did this experiment on a flat plane versus an inclined plane, and then you need to compare. So for example, I'm just going to do A with you, and then hopefully you can kind of apply this way of attacking it to the rest. So it says the parallel weight component. So the reason why it says parallel weight component is because we know in an incline, weight is again Fg, right? So here's my Fg. When we say parallel, we know we mean it parallel to the plane, right? This is my surface I'm on. This is my parallel component. Notice those are parallel, right? So what you want to think about is, what was my parallel weight component before? Once again, I'm going to go ahead and add an X here for this. This is Fgx. Think about a flat surface. Well, here's Fg. If that is Fg on a flat surface, what's Fgx on a flat surface? Well, it doesn't exist, right? Fg is Fgy on a flat surface. It is strictly a y component. So on a flat plane, like we just did, the parallel weight component is, well, 0. Doesn't exist because I'm not parallel to my surface at all. When we start to tilt and go on an incline, then it does exist. So Fgx exists now. It didn't exist before, and now it does when you go on an incline. So what does that mean for the effect? Did Fgx increase or decrease? Well, it increased because it was 0 before, and now it exists. So that's what you guys want to be thinking. In each case for BCD, you need to think about, what was it like on a flat surface versus on an incline. And then you can see if it increases or decreases or possibly stays the same. Okay, so this was kind of a long video, but again, didn't want to leave you guys too out in the dust with me being gone for 2 days. So you can message me questions on Remind still if you have some. I'll be back on Wednesday. We'll take some time on Wednesday to answer questions for things you weren't sure about on the lab. Feel free to talk to other groups, though. It's possible that if your group is really struggling, somebody else is doing well. Be good for the sub. I will see you guys on Wednesday.